where I am now. Very much.
He's in a good university. He's in a little Mecca.
It's in Raleigh, North Carolina. Yeah. Uh-huh.
Yeah, that's why he likes it.
Oh, you mean, oh, gotcha. Yeah, yeah. Yeah.
This,
No, I hate North Carolina.
yeah, right.
So, sure. Okay, sure.
Alrighty, hi everybody. Welcome, welcome. Hi. My name is Kirsten Marie Fox and I'm the program manager at Lakeside, and I'm very excited to welcome you all to our environmental series. We are very fortunate that Jordan Kern has joined us again today, and this afternoon's session is Droughts, Heat Waves, and Air Pollution, Connections with the Power Grid. In this presentation, Jordan will discuss how droughts reduce hydropower production and heat waves increase electricity demand, forcing power system operators to rely more on fossil fuel power plants. Using California as a case study, this lecture explores why air pollution impacts from power plants, fine particulate matter, are highest in hot, dry years. We will also discuss who is most impacted by this extra pollution demographically. Jordan is an assistant professor at North Carolina State University, where he has a primary appointment in the Department of Industrial and Systems Engineering and graduate faculty in Operations Research and Civil, Construction, and Environmental Engineering. In 2022, Jordan received the National Science Foundation's Early Career Award for his proposal titled Navigating a Two-Front Challenge for the Power Grid, Extreme Weather, and the Race to Decarbonization. So not an overachiever at all, Jordan, not at all. Awesome, so everybody, if you wouldn't mind, please turn off your ringer on your cell phone and help me welcome Jordan Kern.
Well, thanks very much for being here on another rainy day. And thanks for having me again to the Lakeside educational program. So I'll jump right into it. And I see some familiar faces from yesterday and some new faces. And so maybe I'll preface this by saying this lecture is a little more technical than the one yesterday. So yesterday I said, what I presented was sort of the first day of class for one course that I teach at NC State. It's not an engineering course, it's sort of a general education class meant to bring in people from technical backgrounds and less technical backgrounds, so it's meant to be a little more accessible. And so what I'm going to talk about today is really narrower and a little bit more technical, which sometimes translates to more boring and less entertaining. So we'll see. But it's a little less broad and more specific about one particular dynamic that can occur related to the operations of electric power systems and their vulnerability to certain types of extreme events. So I would encourage you to stop me and ask questions anytime you have any confusion. I'm not going to go into a ton of detail about the methods behind what we do. I'll explain some of that. But please don't hesitate to interrupt me if at any point you have a question. So let's start with some basics about what we all kind of refer to as the power grid, right? So that really means bulk electric power systems. So many people would regard our high voltage AC power systems that we have in the United States and also in other developed countries as probably the most sophisticated, important invention ever, right? Because it powers and energizes so much of modern life. So what do we mean by this? So it's a network, right? The network is the grid, and it's a network that connects generators or power plants of all different types. That could be fossil fuel power plants like coal or natural gas, or nuclear power plants, or wind farms or solar farms, with the main people, the processes that are consuming that electricity. That could be retail consumers like me and you, or commercial consumers, or industrial consumers of electricity. And so there's different components to the grid, right, that are all really important. So you have power plants, and then as soon as electricity is produced by power plants, it's ramped up to incredibly high voltages and sent out over high voltage transmission lines, and that's all to decrease how much electricity is lost along the way, right, along the transmission lines. And then when it gets roughly to where we want to consume it, right, we ramp it down in voltage twice usually until it gets to low enough voltages so it's going into your house and you can consume it. So who operates the grid? This is a messy, very interesting question. This is the United States, right, the continental United States. The bubbles are who controls the grid. Those are called balancing authorities. So balancing authorities are sometimes electric utilities, and sometimes they are other entities that are more independent, right? They're system operators that might not actually own any assets, but have been charged for just operating the grid, determining how much electricity should be produced to meet demand, if electricity should be exchanged with other areas. In Ohio, you buy electricity from an electric utility, or maybe it's a co-op, but that electricity ultimately is being administered by this big bubble called PJM, which is Pennsylvania, New Jersey, Maryland. It's an independent system operator, which means they don't own anything. They're a nonprofit. They're just in charge of making sure that the electricity that's being produced is perfectly in balance with the amount of electricity that we are pulling off the grid and consuming it in real time. And they also, interestingly in PJM, treat electricity as a commodity that can be bought and sold, which means there's a market and prices can go really, really high if there's scarcity, or really, really low. And we're not going to talk about any of that today. But if you ever, well, a couple years ago, there were like really big headlines coming out of Texas, because Texas also has a market for electricity. It's a little bit different than PJM's, and electricity prices went to like $10,000 per megawatt hour during Winter Storm Uri, which was coincided with some rolling blackouts.
And very limited interconnection.
Right, and so that's the other thing to mention here, right, is that there are 3 physical grids in the United States, right? So you can send electricity from North Carolina, where I'm from, to Ohio in theory, right? It doesn't always happen in practice for a variety of reasons, but you cannot send electricity from North Carolina to Texas, or anywhere to Texas. Texas is an island, and it's partly because they don't want to be regulated by the federal government, right? Because anytime a transmission line crosses state lines, then the federal government has to play a role in overseeing the management of that line. So Texas is electrically an island. In the eastern United States, it's really here, so not quite eastern, right? Everything except for the Mountain West is one contiguous grid. And then the western United States is a grid, right? And they really don't interact at all. And so what we're going to be talking about today is really the western coast of the United States, which that's not where all the people live, which where the majority of people in the western United States live, is along the coastline. And the west coast of the US is very unique in terms of its climate and where it gets electricity relative to the rest of the United States. And so there's some sort of interesting wrinkles about today's lecture that are really just specific to the West Coast. Okay, so bulk electric power systems, i.e. the grid, in the United States, but also globally, face 2 really important challenges, right, that we're going to have to deal with increasingly over the next several decades. The first is, it is the lowest hanging fruit, the first domino to fall, however you want to describe it. This is what has to happen first if we want to like meaningfully deal with climate change, right? And part of that's because there are readily available, mostly cost-effective substitutes for fossil fuels when it comes to generating electricity, right? The sort of prevailing wisdom at this point is that, so let me orient you a little bit. Behind me, I'll stick over here. The pie chart on your right, my left, is where greenhouse gas emissions come from in the United States, which economic sectors, right? So electricity production produces a lot of greenhouse gases because we're oftentimes relying on the combustion of fossil fuels. Then you have heavy industry, commercial and residential activities, building, heating, agriculture, which can include emissions associated with livestock or soil management, and then transportation, which is light-duty vehicles, shipping, air traffic, et cetera. So the prevailing wisdom at this point is that the cheapest, fastest way to reduce emissions close to 0 on this pie chart is to do 2 things, right? The first is zoom into the electricity sector, and this is where we're getting electricity from. Each color represents sort of a different technology, where the dark gray is coal, light gray is natural gas, orange is nuclear, blue is hydro, pink is wind, and gold is solar, right? So step 1 is don't use any more coal. Don't use any more natural gas, so that all the electricity that we're producing and consuming in the United States comes from some source that doesn't directly emit greenhouse gases into the atmosphere. That's step 1. Step 2 is, right, expand this pie, the piece of the pie that's electricity, right, into these other sectors, right? Meaning drive electric vehicles instead of vehicles that use internal combustion engines, right? where you can, in industry, electrify some mechanical processes. Commercial and residential heating and cooling should be electric as well, right? So electricity by itself does not mean no emissions, right? But if behind the scenes all the electricity that we're producing is low emission, and then you start to use electricity to power some of these other processes, it's a way to pretty quickly reduce how much greenhouse gas emissions we're emitting economy-wide. So this is already starting to happen, right? Which is why it's interesting to talk about electricity, because there's a lot of progress that's been made. And so each of these colors represents a different type of power plant in aggregate or category of power plants. And this is tracking on the x-axis, the horizontal axis, time, right? So we're looking at from 2010 just to today, early 2020s. And the colors, right, on the y-axis, the vertical axis, it's showing what percentage of the overall amount of electricity that we produce and consume in the United States is coming from each technology, right? So there's maybe 2.5 things that are interesting here. The first is that the dark brown, which is coal, is rapidly decreasing, right? And then it's sort of switching places with the gold, which is natural gas. So they're both fossil fuels, but newer natural gas power plants they emit basically half as much CO2 as coal plants. So that's in theory, a good thing, right? Substituting coal for natural gas or natural gas for coal. And then the other thing to notice is down here. So the green is going up. That's non-hydropower renewables. The largest, at least historically, the largest source of renewable energy production in the United States was hydropower. But we've already built as much hydropower in the United States as we basically possibly can, because we've systematically dammed every single major river in the United States. So what we have to expand in terms of renewable energy is wind and solar. So that's what this represents in green. So it's growing, and it's growing rapidly in response to all sorts of stuff, right? Policy that makes it cheaper or incentivizes or subsidizes its adoption, more efficient supply chains, easier financing for manufacturers and developers, and real improvements in the actual technologies themselves that make renewable energy cheaper. Now, as we scale up renewable energy, right, it's a little uncertain how much of wind and solar we're actually going to depend on, but it could be as high as 70% of all electricity production and 40% of all primary energy that we use could come directly from wind and solar. There are some important logistical issues to keep in mind when we rely more on wind and solar. First, there are geographical and network constraints, right? So this is a map of the United States, and the colors represent, I think it's average wind speeds in meters per second. I'm sorry, those numbers are basically impossible to read. At 80 meters, right, which is roughly the height of a turbine, right, of a wind turbine. So purple is high wind speeds, right, and green would be low wind speeds. And one thing to keep in mind is that the electricity production from wind turbines is cubically related to wind speeds, right? So small differences in how much wind speed result in very large differences in power production, right? So it is, if you were trying to figure out the best place to build wind in the United States, meaning if it costs you the same amount to build a wind turbine in Nebraska as it does in North Carolina, right? Which would you choose, right, to maximize how much electricity you're going to produce? You'd pick Nebraska, right? There's a section of the Great Plains that has really high sustained wind speeds. And if we wanted to maximize how much wind we would produce, we'd build all the wind turbines there. Oh, and I should also look offshore. Offshore also has higher wind speeds compared to the coast, but it is much, much more expensive to build offshore wind than land-based. Here's a similar map for solar, right? So this is the colors. Warm colors represent higher resource potential, meaning there's more sunlight hitting a panel on average in Arizona than there is in North Carolina, and more in North Carolina than there is in Maine, right? And then this is where people live, right? So the places where we have the greatest wind, and to some extent the greatest solar, are the lowest population density parts of the United States, right? And so right there's a fundamental problem, which is where we make the electricity is not necessarily where people live. And that probably entails massive investment in additional high voltage transmission capacity, which is very expensive to build, politically a nightmare to build. Is the reason why we're not having much success building more. But the federal government is taking steps to try to make it easier to permit high voltage transmission, which is interesting for a variety of reasons. Anyway, so that's obstacle number one with renewable energy. And the other is its variability and uncertainty, right? There's a fundamental difference between relying on a wind farm and having a natural gas power plant where you can push a button and turn it on and ramp it up and down. So this is just two weeks of simulated wind power production as sort of a proxy for wind speeds near the coast of North Carolina, right? So it's pretty variable, right? You don't always get the same amount every hour of every day. There are potentially long stretches, 24 hours at a time where you have very little, right? And so that's an issue, right? Here's a similar figure for solar. This is, I think, a month of solar. Maybe it's 2 weeks of solar. No, 4 weeks of solar.
It didn't rain during the month.
Say that again?
It didn't rain.
Here?
You're not low enough to have a good soil.
Oh, yeah. So this is also from North Carolina, and probably, yeah. So like you can see day-to-day differences, right, in how high the peaks are, which are, that's a measure of cloud cover, right? So even if it's cloudy, you get some. With solar, at least you know when you're not going to have it, right, which is at night, right? So that's a little bit helpful. But both are not just variable, but they're also uncertain. It's one thing if they're just variable, but you could predict multiple days in advance, oh, I'm not going to have wind, I'm not going to have solar. The fact that they're uncertain adds an additional cost for electric utilities and system operators to figure out, well, how much backup do I need, right? What other resources am I going to have to use to try to compensate for this lack of wind and solar when that occurs? The good news is there's lots of solutions here, right, for integrating lots of renewable energy. That could be batteries, that could be redundancy, meaning just build more than we think we actually need. Relying on certain types of generators that can turn on and off quickly, ramp up and down quickly to help compensate for some of the variability in wind. As I said, building transmission, that's hard, but in theory doable. Forecasting, right? Using better, more sophisticated weather forecasting to try to predict in advance how much wind and solar we have. And then the other one is flexible demand, right? Which I'm not really going to talk about at all today, other than to say historically, I mean, electricity is a very interesting thing that we consume, right? It's kind of unlike other things that we consume in that, if you buy food, someone's already made it and put it on a shelf for you. If you buy electricity, someone is making it the moment you use it, right? That's instantaneously. Generators are going up and down to balance out our collective consumption of electricity in real time. Okay, so that's challenge number one for the grid. Oh, yeah. Yes. Yeah, it's a great question, right? And that does tie into the main topic today, which I promise I'll get to. Oh, sure. So the question was that These illustrative examples of the variability associated with like wind power production and solar power production are spatially explicit. They were taken from a site in North Carolina, and the question was, is this generally representative of the degree of variability and uncertainty that you'd see in those same resources, wind and solar, in say Arizona, right, or New York State? And the answer is generally yes, right, on these timescales, right? But the seasonality of wind and solar is very different, right? So like the high wind season in the Midwest is different than the high wind season in California, right? Solar, the seasonality is the same in the Northern Hemisphere. We all get the same amount of, roughly the same, yeah.
With a big difference between summer and winter, if you're in Ohio or in Florida, because of daylight hours.
Yes, right, so but the seasonality, right? So you get more sun in Florida in the summer, you get more sun in Ohio in the summer, but oh, you're saying that, oh, so the difference between winter and summer in terms of, right. Right, right. So there are differences geographically that mostly have to do with the seasonality, right? But day to day, hour to hour, this is really typical, and this is really typical.
Based on cloudiness, rain, snow, that covers your solar cell.
Than this.
Yeah, because you can come close to zero on any random day.
So it depends. I think, you know, if you're talking about like snow that's covering solar panels or like really, really overcast days. Yeah. Does that answer your question? Okay. Other questions? Okay.
The other thing,
Yeah.
go back to solar for a minute.
Sure.
Notice how pointed those are.
Yeah.
Peak solar is about 2 hours before and after solar noon, and it drops rapidly
Right.
on each side. We always talk about the installation based on the breaking of the panels.
Right.
But that's at peak sun with a perfectly clear sky.
Right. So the point that he's making is that like if you were to install a 4 kilowatt panel on your roof or something like that, the duration of when you're actually producing 4 kilowatts is very short and somewhat dependent on the weather conditions, right? It would require a clear day, and then even on that clear day, you might only be producing 4 kilowatts for a couple of hours, right? Does that make sense? Okay.
Also, why batteries make an awful lot of sense.
Yeah, yeah, right. All right, so that's challenge number 1 for the grid. The challenge number 2, challenge number 1 is seeking to address climate change, right? Challenge number 2 is dealing with climate change, right? Because there's so much that's already baked in. Right now, the game we're playing is trying to mitigate the worst possible climate futures, right? But given how much greenhouse gas we've already put into the atmosphere, we are going to experience increased severe weather in the future in a variety of different areas. And one of the most vulnerable critical infrastructure systems we have to extreme weather is the power grid, right? And so that can come a variety of different ways, right, depending on where you live in the United States. So I'll go through a couple of examples. The first is wildfire, right? So wildfire is a tricky example because it can directly influence or negatively impact the operation of the power grid. And it has also been famously started, right, by the operations of electric power systems. So the PG&E, Pacific Gas and Electric, went bankrupt due largely to liability associated with starting a wildfire that killed about 100 people and caused a lot of damage. Extreme temperatures, both hot and cold, right? So we typically associate climate change with very hot temperatures, although it depends. Yep. Oh.
Go ahead, I was just chuckling.
Okay.
Because if
So yeah, so one of the less well understood aspects of climate change is how it affects the behavior of the jet stream. A really wavy jet stream, which is the sort of, right, it can pull cold weather down into the eastern United States potentially more frequently. So you could weirdly have a future where on average temperatures during the winter are a lot warmer, but occasionally that could be marked by very, very, very cold episodes that people aren't really prepared for. So extreme temperatures increase our consumption of electricity, and if it's really hot or really cold, it can actually break different components of the grid. Extreme storms, especially hurricanes. Hurricanes are the #1 cause of massive power outages in the United States. Usually that's due to high wind, but it can also be due to flooding as well. So this is a picture of an electrical substation that's being flooded. Drought, which we're going to talk about today. The main influence of drought on electric power systems happens in the western United States, and it's because there's not as much water that's available to produce hydropower, and that means that the system operator has to use something else, if it can, to produce that electricity. And then extreme winter storms are increasingly playing a role. I mean, I mentioned the Winter Storm Uri in Texas, and one of the main ways that this can influence power systems is by first impacting natural gas infrastructure, which disrupts the flow of fuel to power plants and can have kind of a cascading influence. So I've covered some of this before, but I think it's really important to realize that the power grid is a really unique engineered system, and the way it behaves in response to adding renewable energy to the grid or being affected by extreme weather is related to the physics of the grid. And so I just wanted to sort of walk through some of what that means. The first I mentioned before, the grid is a synchronous machine. The supply and demand for electricity has to be perfectly in balance all the time, everywhere throughout the entire grid. So it's not like any other, commodity or a product that you consume. Demand is inelastic, meaning at no point are you receiving any information about the price of how much it's costing to produce the electricity that you consume. And it makes it difficult to make any sort of price-sensitive decision. So like if you went to the grocery store and the cost of milk was 100 times what it is tomorrow than today, right? You might say, well, I'll buy a substitute product. I'll buy almond milk, or I'll drink bottled water or orange juice. And electricity is different. We just use it, and it's utility's job to meet our demand instantaneously. So there's no flexibility on the part of consumers about using electricity typically. There's not really available storage on a large scale. That's starting to change. That means that the demand for electricity that we have needs to be met instantaneously, right, by power plants that are producing electricity. It's also, relatively speaking, an ancient infrastructure system, right? There are parts of the grid that are over 100 years old, and it's really complicated and stuff breaks all the time. It's highly interconnected and continental in scale. Remember that map I showed at the beginning? And also electricity can travel at the speed of light, which also makes it different than any other thing that you consume. So all of this put together really influences how the sort of geographical scope of the impacts of things like extreme weather or accidents, right? So like a bad thing can happen in Ohio or New England or the Gulf Coast, and it could impact me in North Carolina. Really easily, this happens all the time. And so we're gonna talk, this is me sort of setting the stage for the actual topic for today. With all of this in mind, right, I wanted to walk through sort of a narrower example about how extreme weather can, given the interconnected nature of the power grid, have some interesting effects that relate to air pollution and talk about, in some cases, the unequal exposure of different people to that air pollution. This is a project that was funded through the National Science Foundation that I led, but was joined by great colleagues, Professor Andy Yates at UNC Chapel Hill. He's an economist. Paige Weber, who's at UC Berkeley in California, also an economist, and my PhD student Amir, who is going to graduate this fall. This paper was published a little over a year ago, and when it came out, it got a lot of press. It was covered in the LA Times because we focused on California specifically. Okay, so let's talk about air pollution. Air pollution in the United States is a persistent public health issue, right? Especially when we talk about, we're not going to talk about CO2 today, although the EPA does consider greenhouse gases like carbon dioxide an air pollutant. We're really talking about what the EPA would call criteria air pollutants, pollution that directly harms human health, right? CO2, in the grand scheme of things, I think people would view as a very severe risk, right, that could cause public health, but sort of indirectly by causing climate change. Fine particulate matter, right, and ground level ozone directly contribute to tens of thousands of early deaths, premature deaths every single year. 50% of the pollution, of that pollution in the atmosphere comes from the combustion of fossil fuels. And then 10% of that 50%, so 5% overall, comes from the burning of fossil fuels at power plants. So it's a relatively small piece of the pie that we're talking about. But this last bullet is what we're talking about today. So the air pollution, fine particulate matter, and ground level ozone that stems from the combustion of fossil fuels, coal and natural gas, in some cases oil, at power plants. So the good news, and I talked about this yesterday, the good news, I mean, when the context that we talked about yesterday was like thinking about climate change as an environmental problem relative to something like clean air or clean water. Clean air and clean water in the United States, right, in response usually to regulations and policy, are great success stories on average, right? The air and the water in the United States, on average, is cleaner than it's been in at least 30 or 40 years, and that's what this is showing, right? So the different colors are different pollutants and different ways of measuring those pollutants on average, or measuring the highest value taken over, measured over shorter time scales. And so the green, and the gray dotted line, right, across that's going in the middle at 0%, is the official air quality standard, the National Ambient Air Quality Standard in the United States. That's the rule that the EPA has in place. And what you can see is that over time, we're getting much, much better, right, at producing less, in particular, fine particulate matter and ground level ozone. So that's good news on average, right? The issue is that it's not good for everybody, right? The places where air quality have improved, or air quality has improved unequally across the United States, and exposure to poor air quality is unequal in the United States. And so part of that has to do with the legacies of systemically racist housing policy, like redlining. So this is a map. This is from a paper that was published in 2022. And up in the top, you can see maps of different urban areas that are color-coded, right? And so these maps are redlining maps. And if you're not familiar with the process of redlining, what that means is a practice that was pursued throughout the 20th century, where banks, so like savings and loan entities and insurance companies, deliberately denied access to mortgages and insurance for people of color in certain communities. And on paper, the reason was because they viewed it as a financial risk. Like if you're a bank, you don't want to give somebody a loan that's less likely to pay you back, right? But this was a practice that has been shown to have been unjustly applied, right? If you had two different families that had the same credit score, the black family wouldn't get access to the insurance policy or the loan. And in the long run, what that meant for black communities is that they were unable to build wealth, right? It's one of the main reasons why we have a difference in wealth between black people and white people in the United States, is because housing, owning a house, is a great way to build wealth, right? You avoid paying rent. It forces you to save, and then you have an asset that you can either liquidate or pass down to a future generation. Here, we're not as concerned necessarily with the impacts of that policy on wealth disparity, but if you have certain communities where home ownership is less rare, or is more rare, right, and people aren't improving their houses or their communities because they don't own the houses, that keeps the value of the property in those neighborhoods lower. So if you're an electric utility and you're trying to build a power plant and you're looking around for the cheapest place to build the power plant, you build it in the communities where the land and the property costs are lower, and that's how power plants get predominantly built in communities where it's mostly people of color. And so this is a figure that's just showing in general that air pollution tends to be higher in those same communities, or communities that were more profoundly impacted by redlining. So that's one thing that we know, right, which is that communities of color tend to be more exposed to air pollution, and it dates back to the process of redlining. We also know that air pollution doesn't affect us equally through time. Right? So sometimes there's higher air pollution than others. And there's a lot of evidence suggesting that drought, because it reduces the availability of hydropower and causes system operators to depend more on fossil fuels, increases air pollution. And also extreme temperatures, because we're using more electricity. And that electricity has to come from somewhere, and often it's fossil fuels. So let's think about how heat waves and droughts combined could influence air pollution and people's exposure to air pollution. So this is obviously a very simple representation of a city and a power grid, right? So you have some hydroelectric dam, and then you have fossil fuel power plants, and collectively what they're trying to do is meet the demand of consumers in these urban areas. So what happens during a drought and a heat wave, which don't always happen at the same time, but on the West Coast, they are much more likely to, right? Like they come in the same year and the same time. You have decreased hydropower production, increased demand for electricity at those cities, and if you remember that map of the United States with all the bubbles and the balancing authorities, each one of those system operators, the balancing authorities, has one mission, right, which is to minimize the cost of meeting electricity demand in real time, right? So it's sort of like a mathematical optimization. They take all the power plants they have, they're all connected through this network, they know where people are using electricity, and their job is to figure out the absolute cheapest way to get electricity from the power plants to our homes, right? And often that involves a choice of which power plants to turn on when, right? So in general, coal-fired power plants are cheaper, right? Coal is cheap. Coal is easy to store. It's domestically abundant, right? So the electricity coming from a coal plant itself might be cheap, but they're much dirtier, right? They produce more CO2 emissions, but also other types of criteria air pollutants. So if there's a drought and a heat wave, the system operator might say, well, my job is to make sure demand for electricity is met, right? At the lowest possible cost, I'm going to turn on the coal plant, right? And if they turn on the coal plant, depending on where the coal plant is located and prevailing wind speeds and the geography of the region, that might result in an accumulation or a buildup of a higher concentration of fine particulate matter and ground level ozone in this particular city, right? So what do we do about that? There are lots of different options, one of which might be just don't use coal plants ever, right? But in the current, sort of mix of what technologies we employ, coal still has a large role. And so one idea, and this is an idea that we've used in other types of, to manage other types of pollution, would be to penalize or tax all the power plants based on how much they damage people, right? So you could figure out for each one of these power plants, right, the coal plant and the natural gas plant, for every unit of electricity that it produces, how much pollution does it produce? And of that pollution that it produces, how much does it impact people, right? And then there's some calculations that public health people do where they try to figure out, based on your exposure to certain levels of pollution, how likely are you to have to go to the hospital because you have asthma, right? Or because you have some other pre-existing health condition that's exacerbated by exposure to fine particulate matter, right? And so they come up with basically a dollar value for how much it costs you every time you're exposed to pollution. And so in theory, right, you could then say, all right, well, the coal plant, every time it produces 1 megawatt hour of electricity, it causes more damage than this natural gas plant that's further away, right? So if that's the case, right, and you penalize the coal plant more than the natural gas plant because the coal plant is dirtier, then the system operator who's in charge of this whole thing, if they're still trying to minimize the cost of meeting demand for electricity, they might choose the other one, right? As soon as you incorporate the actual cost of pollution, now the coal plant looks more expensive, right? Because you're including the cost that ordinary people are incurring as a result of the health effects. The question is, can you do that if you're also trying to make sure that the power system is reliable, right? If you are, will this work in a heat wave, right? Or a cold snap or a drought? And so that's sort of the basis for this experiment that we did. And there were 4 questions we wanted to answer. The first was trying to figure out if droughts and heat waves in the western United States do cause this increase in air pollution. We kind of knew the answer to that before we started, but we just wanted to confirm it. The second was, and we also kind of knew this, can we confirm that air pollution exposure and damages caused by air pollution are impacting people unequally across the population? How would taxing emissions impact those dynamics? Would air pollution exposure go down? Would black people and white people be more equally exposed? I shouldn't just say black, it's black or brown. And then if we implement these sorts of taxes, right, would that influence our ability to meet demand all the time, right? So there's really 3 things everybody wants when it comes to energy, which is you want it to be cheap, you want it to be reliable, and then the third one is you want it to be sustainable, environmentally sustainable, right? So is there a conflict here between keeping energy cheap, reliable, and clean? Please stop me if you have any questions. I'm gonna gloss over some stuff. Okay, so what we did, so let me orient you first. On the right, this is a very simplified representation of the West Coast bulk power system. There's 2 main regions. There's California, which is the 8th largest economy of the world, right? So economically very important part of the United States. And then the Pacific Northwest, which is this purple region, right? All the little dots represent the exact location of electric power generators of different types. The dark blue dots represent hydroelectric dams. So they're all scattered all throughout the Columbia River Basin, and also in the higher altitude Sierra Nevada mountains in California, right, which is east of the Central Valley. The red represent thermal power plants, which is usually natural gas and occasionally coal on the West Coast. Gold represents the location of large solar plants, so not rooftop solar, but large solar farms. And then the green or teal represents wind farms. The black dots are essentially the footprints of individual electric utilities, right? So we're not modeling things down to the individual household level. We're sort of aggregating. So like these two in the middle of California are PG&E. That's the company that went bankrupt, but they still have customers and assets. And then there's Southern California Edison, San Diego Gas and Electric, and then the black dot at the top sort of merges together all the electric utilities that serve people in the Pacific Northwest. The lines connecting all the dots are high voltage transmission, let's say pathways, because they're sort of merging together lots and lots of lines all at once. So what we did is we built my group builds software, right? So we build computer models. They're kind of like video games, I guess, that simulate the way that this system is operated hour to hour in real time, right? And it's kind of like a game in that there's a goal, right? The computer program has a goal of finding the lowest cost way to meet demand every single hour. And so there's a cost associated with turning on all these different power plants, right? And ramping some up and down, right? And there's a cost associated with sending electricity on these high voltage transmission lines. And so what the computer program does is it finds the lowest cost, mathematically the least cost, optimal way to schedule electricity production at every single power plant along the whole West Coast in order to meet demand for electricity that's constantly fluctuating, right? So this is what electricity demand looks like in an average year in California. On the horizontal axis is hours. There's 8,760 hours in a normal 365-day year. And then on the y-axis, it's measuring aggregate total electricity demand that everybody in California is contributing to each hour of the day. And so you can notice there's seasonality here, right? Changes in electricity consumption throughout the year all over the United States are mostly driven by heating and cooling demands, right? Now, it looks different here than it does in the Pacific Northwest and California and Ohio and Florida, et cetera. But you can see that summer in California is the high demand period of the year. They have limited cooling needs, so everybody's just turning on air conditioning in the summer. And so the computer game, right, the simulation, if it's trying to meet this demand, right, it's like that's the rule we place on the simulation is that it has to turn on enough power plants so that it meets this demand every hour. In the spring, it might not have to turn as many power plants on. But in the middle of the summer, because demand is really high, it has to turn on many, many, many more power plants than in the spring in order to meet that demand. Now, it doesn't just have to rely on fossil fuel power plants, right? It also makes use of what's other things that are available, right? Which would be hydropower and solar and wind, right? So this is a time series of how much wind is available for that same year in California, right? So it doesn't come close to meeting the black, right? It's pretty far down on the y-axis, but this is like a useful contribution, right? Any wind that's available means you don't have to turn on the fossil fuel power plant, right? And so the arrows are indicating like this is a high wind period of the year where maybe because more wind is available, they don't have to use as many fossil fuel power plants. But then there's a section later on in the year where wind is really low. Well, that would represent likely a time where they might have to turn on an extra fossil fuel plant. And this is a similar time series for solar, right? And then also hydropower, right? So the wind and solar and hydropower the system operator uses, and whatever's left over, whatever demand is not met by wind and solar and hydro, that's what the computer game is optimizing. It's trying to figure out, well, I've used up my wind, I've used up my solar, I've used up my hydropower. I'm going to have to turn on some fossil fuel power plants, right? What's the cheapest way for me to do that and meet electricity demand? Okay. Make sense so far? Any questions? Yeah.
Does 3 ever make enough power for the demand?
Say that one more time.
If you add all 3 of those combined, do they ever add enough demand to meet electricity?
Oh, in California? That's a great,
California has actually had hours, I mean, several hours in a day where they use completely renewable resources.
yeah,
But not every day, not anywhere close. They've had a few days. I live out there, I know that.
yeah,
And I live in the Central Valley where it's really hot.
right.
But, yeah, they've had a few hours now where they've used, they've used renewables for the whole thing, but rare, and of course it's not at night.
It's rare. It does happen regularly, especially if you add in the contribution of nuclear power, right? Because nuclear power plants in the US, are used very inflexibly. You turn them on, you ramp them up to 95% capacity, you leave them on all the time for a variety of reasons. So if you added hydro and wind and solar, during some of these periods where demand is really low, you do get to like meeting all of demand with, let's say, zero carbon resources, not necessarily renewable. Does that make sense? But that is happening more and more as wind and solar is constructed in California, and it causes some interesting issues where they have to forcibly curtail renewable energy because there's too much being produced. Okay, so the outcome of this computer model is the best way, the optimal least cost way to operate this system, right, in order to meet electricity demand. And what that gives us is a schedule of generation production at all the power plants. We know how much electricity is flowing through all the transmission lines. The main thing that causes these dynamics is weather, right? Changes in stream flow influence how much hydropower is available. Air temperatures influence how much demand people in California have for electricity. Wind speed, as I said before, directly controls how much the output from wind farms there are. And then solar irradiance influences how much electricity you get from solar panels. So if we wanted to figure out or simulate this computer program, right, under lots of different conditions, right, what we try to do is figure out what is like a representative set of weather information that we can use to sort of like force through the model to see how it behaves under different circumstances. And the tempting thing to do for utilities or system operators is to just go back in time and take as much weather data as available and say, well, that's representative, right? Here's the problem with that, right? So one idea would be to just take, okay, let's take the last 50 years of weather data and see how the model or the game sort of simulates under those conditions. So anybody know the chance of rolling 4 ones with 4 six-sided dice off the top of your head? The chance of rolling 1 1, right, is 1 in 6. The chance of rolling 2 ones is 1/6 times 1/6. 3 ones would be 1/6 cubed. 4 ones would be 1 out of 1,296. So rolling 4 ones with 4 dice is a rare event, right? But it could happen. Yeah, right, sure. They're independent, right? So now think about weather variables, right? The things that ultimately are controlling the dynamics of electric power systems as random variables, like dice, individual dice. And it's not, so we have wind speed and solar irradiance and air temperatures and water availability, and not just in one place, but in lots of places, right? And so if you're an electric utility, right, and you're deciding, well, what's the worst case scenario, right? It may be tempting to say, well, let's go look at the last 50 years of what's happened and find the worst year, the hottest, driest year, and we'll say that's the worst case scenario, right? But if you've only rolled the dice, 4 dice, 50 times, how likely is it that you got 4 ones? Very, very unlikely, right? So, and this doesn't have anything to do with climate change, right? It has to do with whether historical data accurately captures the probability of bad events and risk just today, right, in the system that we have, the climate that we have. So if what we're really trying to understand is like, what's the worst that could happen in California next year, just using the last 50 years of data is like putting blinders on purpose, right? You're just deliberately ignoring the worst case that could happen. So part of what we did, we have this computer model that simulates the way this whole system works. The other kind of neat thing that we did is we built this other kind of little game that basically rolls the dice, right? It takes weather data that we've already seen, and that's sort of what determines the likelihood of rolling a 1 or a 2 or a 3 or a 4, right, is what we've observed before. But then we just roll the dice over and over and over, and we get new weather data, right, that looks kind of like the weather data that we've seen, but we're increasing the chances that we roll 4 ones, right? Does that kind of make sense? Okay. Okay, yeah.
The 4 ones being drought, low wind.
Yes. High temperatures and yeah, right? So that's what you're trying to do is figure out, okay, like if we roll the dice many, many, many times, eventually we're going to get some years that are worse than any that we've already seen. Just not thinking about climate change, just the fact that weather is uncertain. It's a dice game, right? And if you play the dice game long enough, you're going to roll 4 ones. Okay, so that information gets passed through the computer model. So instead of simulating the behavior of the system under 50 years, now we have 500 years to play with. And what we really care about is, remember, this game is finding the best way to meet electricity demand by controlling all the different power plants. And the best way is going to result in some power plants being turned on, fossil fuel power plants turned on, producing electricity, producing pollution, fine particulate matter, and ozone. And then we want to track where it's going, right? So what we use is a very simplified air quality model, right? It assumes that the location of all these little red dots are smokestacks, right? And when the model decides to produce electricity at each one of those red dots, pollution is coming out of that smokestack at a rate that depends on the age of the power plant, what technology it's using to combust the fuel, what fuel it is, et cetera. We know the prevailing wind speeds, right? So we know wind speeds are blowing all different directions all the time, but we assume that there's an average direction, right, measured over time that is dispersing the pollution in a given, transporting the pollution in a certain direction. And then as pollution travels, not only is it traveling in a direction, it's gradually spreading out like a gas spreads out in an open container, right? So it's spreading out this way and spreading out this way. Crickets. Okay, and so what that type of model allows us to do is estimate how pollution is transported across space and across time. So this is just an example of kind of what that looks like. This is from Andy Yates, the economist at UNC. Put together this study that's unrelated. Do you all remember when there was this scandal about Volkswagen diesel cars evading? Yes, right. So this is measuring the unaccounted for damages, public health damages associated with that scandal, right? So it's figuring out who owns all these cars, where were they being driven, where are the emissions coming from, and then how are those emissions transported to different communities, and if you sort of trust the public health estimates, how can you translate those extra emissions into trips to the hospital, et cetera, et cetera. So we get something, they did this study using this same kind of model, and so we took, because Andy was on our study, he was like, well, let's use it for this, right? So instead of having a map that shows where pollution is distributed from unregulated, Volkswagen diesel cars, right? Now we have emissions that are being transported from power plants, and we're tracking who is exposed to those. Okay, and one of the things that we're particularly interested in is demographically who is most exposed to this pollution, right? Is it equal? Does everybody get exposed equally, or are there certain demographic groups that are being disproportionately impacted? So how we measure that is through, we looked at racial inequality and pollution burden. Racial inequality is trying to figure out, are black and brown people disproportionately impacted relative to white people? Pollution burden is saying, are people that are already exposed to pollution from other sources disproportionately impacted to extra pollution from power plants? The way we are evaluating that is saying, so this is a map of California, and we're evaluating this on a county level. So the colors on the left represent the percentage of the population in each county that identifies as a person of color, right? So the red values mean mostly white counties, and the gray and dark gray counties mean mostly counties that where a majority of the population identifies as a person of color. So the way we would evaluate this is if you can predict how much exposure to pollution you get as a function of how white your county is or how black or brown your county is, that's a problem, right? You shouldn't be able to predict it based on the demographics of the county. And so the way we would measure that is with a correlation, right? So there's 58 counties, I think, in California, right? So we take all 58 counties, and we'd say, on the x-axis, what percentage of the population in that county identifies as a person of color? And on the y-axis, we'd say, how much pollution do you get, right? And if it's a positive perfect line, that's really bad, right? That means that, as a function of how black or brown your county is, you get more pollution, right? If it's in the middle, if the correlation is 0, it means that there's no relationship, right? That you're either exposed to pollution or you're not, and it doesn't have anything to do with the demographics of your county. And if there's a negative correlation, it means that, weirdly, right, the whiter your county is, the more polluted you are, right, instead of the opposite. So this is how we're going to try to measure some degree of inequality. Ask questions if any questions now. Well, maybe we'll stop. Yeah.
What's the difference between like environmental social justice communities versus community service now? It looks like you're just looking at race, but there's so many other factors.
Yeah.
I wasn't sure if there's a difference or if you're just simplifying it.
Simplifying it, although those are very highly correlated, right? So I think you're absolutely right that communities that have been identified as vulnerable from an environmental social justice perspective are not the same as black and brown communities, but they're pretty highly correlated in the United States. And then we're also looking at, these are also overlapping. The green is a measure of pollution burden. So that would be communities that we don't care what their demographic makeup is, but it's just thinking about what communities are already experiencing high degrees of environmental pollution. And we're going to try to look to see if that also is highly correlated with who receives pollution from these power plants. Does that make sense? Okay, yeah.
One of the things, I live in Tulare County, which is
Uh-huh.
to the, right?
Yeah, yeah.
Lower part, and it's about 70% Hispanic.
Right.
And we have, between Tulare County and Fresno County, is the worst air pollution in the country, typically. And Visalia, where I live, has been named a few times before over the years.
Yeah.
And the problem they have there is you've got that big mountain range,
Right.
National Park is right next to it.
Yeah.
So all the pollution
Gets
from
trapped.
prevailing wind, it takes all that pollution from the coast, and our county gets yelled at by the state all the time because we have the worst air, but it comes from the
Coast.
And it gets to those mountains and they can't get over the mountains, so it just recirculates.
Yeah.
And you hear me cough all the time. It's probably partially why. But yeah, in the demographics, they're all mostly lower income farm workers.
Right.
That's the area.
Yep.
So you look around and you can't look anywhere without seeing solar panels. Every school has the whole parking lot covered with solar panels. Every dairy farm must have, I don't know, 10, 20, 30 acres of
Yeah.
solar panels. But so they
They do.
Energy there, but they also have the worst air in the country.
That's right. Yeah.
It's kind of a paradox.
It is. It's a really interesting part of I've spent a lot of time in Central Valley. It's a very interesting place.
Yeah.
Okay, so stop me if you have any questions. Because these are going to be a little dense, unfortunately. All right, so the first question was, how do droughts and heat waves impact air pollution, damages from air pollution, regardless of who's exposed? Like I said, we have this model, and we rolled the dice for 500 years. So that means we have 500 years of data, 182,500 individual weather days, right, that we can test and evaluate. So one thing that we can do is sort of rank these days, right, in different categories, right? If we have a long list of 182,500 days, we could see which one's the best, which one's the worst in terms of different things, right? So that's what we're going to look at here, where the colors represent sort of your rank or your percentile, right? So red means higher values, cool colors mean lower values, and let's first look at demand for electricity in California, right? So instead of one single year, right, this is 500 years of data, right? And the colors sort of represent the probability of having a value of electricity demand on the y-axis any given day of the year, right? So on January 1st, right, the median 50th percentile is that black solid line, right? The very highest demand value is the red, seen over 500 years. The very lowest demand value on January 1st is the dark blue, and then most of the data is in the middle, right? So it's kind of like, if you're familiar with like a bell curve or a probability distribution, most of the information is in the middle, right? And then the tails of the distribution contain more rare but plausible extremes, right? Lower probability events. So the interesting part is actually in the summertime, right? We know demand for electricity goes up in California in the summer because of exposure to heat. Everybody's turning on their air conditioner. And the red tells you basically the worst case scenario. That's how high electricity demand could get in California if you roll the dice 500 times. This is looking at total annual demand for electricity. This is a histogram. So it takes all 500 years of data, right? And it tells you where are you, this is how much electricity is consumed on the whole year. Is it a lot of electricity that's consumed in a year or not that much? And then on the y-axis, it tells you frequency. So it's taking 500 years of data and putting them into bins, right? Yeah?
This is based on constant population.
Yes. Yeah, no, we're not assuming, the only thing that we're experimentally controlling, right, is the weather year. We're not saying demand is going up over time due to climate or population. We're not adding wind panels or solar panels. We're taking a snapshot of California today and then rolling the weather dice 500 times. Yeah. So we have some years that are really high demand, some years that are really low demand, right? And then we can look, so that's that same information, right? So the top one kind of shows you how demand for electricity can change throughout the year in California. And the bottom one shows you the range of values year to year, right? Versus a low demand year versus a high demand year. This is the same kind of information, but for how much hydropower is available in California. Now, California is mostly, they get almost all of their precipitation that falls as snow. And it falls in the Sierra Nevada mountains, and then it melts in the spring and summer. And as all the water is moving downhill, it goes through turbines at hydroelectric dams, and that's what produces electricity. So that's what gives it this sort of distinctive seasonality, where hydropower production is higher in the winter, spring, and summer, and it reaches this low point in the driest part of the year, which is like September and October. And similarly, you can have really dry years or really high or really wet years. And now let's look at air pollution damages, right? So this is calculating human exposure to air pollution every single day of 500 different years. And you can see that it peaks, like the worst air quality days are late summer, right? So the highest red spikes and the air quality days for California are in the late summer, early fall. And then you also have a wide distribution of air quality years, right? Some years are good, some years are really bad, right? And we can actually look into, so I'm gonna sort of zoom into A and B here, right? Let's look at A first. A is the year with the lowest pollution from power plants. Over the whole 500 years, this is like the best case scenario. So here's what's happening, right? Because we're taking weather data all over the West Coast, and that translates to how much wind is available and solar and hydro and how much demand, and that goes through a model that operates the system, we can track not just how much pollution is happening, but like what are the weather conditions that in this case lead to very, very low pollution on the West Coast. So the colors represent, is it like higher than average or lower than average? Green is lower than average, and then the magenta purple color is higher than average. So the key things to take away here for a year with very low air pollution from power plants is the temperatures, right, are all green, meaning it's a really mild year on the West Coast. Not a lot of heating demand, which means in the summer, people don't use their air conditioning that much, which means the electricity demand is lower, and we don't have to use as much fossil fuel, or as many fossil fuel power plants to produce electricity. The other key takeaway is the red piece, right? That's all, or so the stream flow. Those are all red triangles, which means in this particular year, not only were temperatures really mild, but there was an enormous amount of water in the Pacific Northwest and California, which translates to lots and lots of hydropower production, which means that you don't have to use fossil fuel power plants nearly as much, right? And so this map here is showing the location of every single one of those fossil fuel power plants in California. The size of the circle tells you how big of a power plant it is, what its capacity is. And the color represents, like relative to normal, how much electricity is it producing. So green means way, way, way less than normal, right? And that translates to this last map here, which is tracking air quality damages for individual populations on a county level. So it being green also means that relative to a normal year, these conditions, which are low temperatures, so really nice weather, right, and a lot of water, means that you get the lowest air pollution from power plants out of the whole 500 years, right? This is the worst year of those 500 years, right? And it's basically the opposite. Instead of low temperatures everywhere, it's really, really high temperatures everywhere, meaning everybody's using a lot of electricity for air conditioning, especially in the summer. That increases demand for electricity, and that demand for electricity, unfortunately, can't be met by hydroelectric dams because all those triangles are green, meaning it's a severe drought. There's not water in the Pacific Northwest or California. And as a result, all those same fossil fuel power plants in California have to turn on way more than normal, and then air pollution throughout the Southwest increases. Make sense? Yeah?
The solar can't make up the difference from the hydro?
In this case, solar is higher than normal, right, which is good, but it's not nearly enough to make up the difference for the hydro. Yeah. Right. Yeah. And also, well, yeah, I'll leave it there. It's a little complicated. Yeah. Okay, so more complicated stuff. So that was a way of looking at, okay, like what's a good air quality year, what's a bad air quality year, right? And what's causing that? Like how can we visualize what are the conditions on the ground that are leading to higher levels of air pollution from fossil fuel power plants? This is kind of doing the same thing, right? It's a different way of trying to figure out when we see higher air pollution, what's causing that? And so we're going to use what's called a correlation matrix. So these are all different things that we wanted to measure. And CAISO, C-A-I-S-O, just means California. And PNW just means Pacific Northwest. So it's the same list of stuff on the y-axis vertically as it is on the x-axis horizontally. Where they meet in the middle will tell you some information, right? So a positive correlation is going to look red. A negative correlation is going to look blue. Positive correlation means that if A goes up, B goes up, right? Negative correlation means if A goes up, B goes down, right? So for example, if we see a blue square between Pacific Northwest hydropower and local air damages in California, that means that when there's not enough water in the Pacific Northwest, they don't produce as much hydropower, they send less of that down into California, and as a result, power plants in California have to produce more electricity, and they increase how much air pollution reaches people in California. Here's another example, right? So if we see a red dot here, this would represent high demand for electricity in California being positively correlated with racial inequality, meaning the degree to which the demographic makeup of your county predicts how much air pollution you get gets worse as a function of how much electricity is consumed in California. So here's what it looks like. And I would just say, just pay attention to the stuff that's in the black dotted or dashed box, right? So we're looking at the first dashed box here, right, is showing the correlation between air quality damages in California and how much hydropower is produced in the Pacific Northwest, how much hydropower is produced in California, and demand for electricity in California. So this is kind of what I just showed you. The drier it is, both in California and the Pacific Northwest, the more fossil fuel power plants are used in California and air pollution increases. The higher demand is for electricity in California, which is almost entirely driven by air temperatures being high, the more power plants have to be used in California and the higher air pollution goes. The second column here is specifically measuring the relationship between air temperatures and electricity demand and water availability and hydropower production with racial inequality in the distribution of air pollutants. So what this is suggesting is that when you have a drought or you have heat waves in California, extra air pollution is produced because you have to use more fossil fuel power plants, and that extra air pollution is disproportionately impacting people of color, right? So why is that? Why would it be that when there's a drought or a heat wave in California, or if there's a drought in the Pacific Northwest, and power plants in California fossil fuel power plants in California have to increase how much electricity they produce to help meet demand, why is most of that extra power pollution impacting people of color? So this gets back to redlining. So this is another complicated figure. So each row of this figure from the top to the bottom is a different county in California. There are 58 in total. There's 221 different fossil fuel generators, which are going to be the columns. And then each row is organized. The counties are organized from top to bottom based on their demographic makeup, right? The counties at the top are the whitest. The counties at the bottom have the highest percentage of their population that identifies as person of color. Here's where the power plants are in California, right? So the black dotted line separates majority white counties from the majority of people of color counties. So it's not all located in counties that are majority of people of color, but it's mostly located in those counties. And the color of the individual dots or squares represents how damaging those particular power plants are. So the story is actually pretty simple. Oh yeah, go ahead.
Is that number of power plants or capacity of power plants?
Number. Yeah, so that's a good point.
A 10,
Yeah. So this one could be like, yeah, this could be like 1,000 megawatts, and this one could be 1 megawatt, and we're not distinguishing between the two. Yeah, good point.
that would be interesting.
It would be interesting. Yeah, we could look at like how, you know, the size of these different power plants, for sure, right? I'm not sure it would change the story too much. Yeah.
The story would be the same, it might be a little more dramatic.
Yeah, yeah. So it's not super surprising, right, what we're noticing, which is that for a system that depends a lot on hydropower, the less you have, the more you have to rely on fossil fuels. The hotter it is, the more you have to rely on fossil fuels. And given that most fossil fuel power plants are located in communities that are majority black or brown, that is who absorbs most of the pollution when this happens. Yeah?
I look at everything in very simple terms.
Mm-hmm.
And if a power plant is put in a black neighborhood, it seems to me that the state has certain requirements, and also the federal government is trying to be there. So it seems to me very simple to just say, no, can't put it there.
Yeah, you know, I think that I'm not an expert, but I think the communities that are disproportionately impacted in general have the weakest political voices and economic power in the U.S. Yeah. Yeah, and so you got to put them somewhere. And I think in general, the practice has been we'll find the lowest cost way to do this, right? And so I think this is, yeah, yeah. I think, yeah, I don't think anybody wants a coal power plant in their community, right? And so like historically, what we've done is put coal plants. Well, yeah. I mean, I think it's a. Say that again.
It changes with time. We used to put them close to cities.
Right.
Now we get them as far away
From people.
as we can.
Yeah.
And I don't think California has any coal left
That's correct.
in the state.
Yeah, this is almost all natural gas.
The other
Yeah.
thing that's happened, if I built the plant 50 years ago, the neighborhood has also changed.
Right.
Because the plant's there.
It becomes less desirable. Yeah. Yeah.
It's not gonna- It becomes more minority
Yes.
driven because it's less.
That's a great point.
Yeah.
Yeah.
It's not that we necessarily started there,
Right.
but we are today.
Yeah.
I'm going somewhere else.
Okay.
Number one, when did you start doing this study? Because I've followed the climate up and down the West Coast for the last 10 years.
Yeah.
What we're talking about, that flow of the ice, we've been watching the water come down.
Oh, good. Good, good, good. Yeah, yeah.
And that has been impacting. What I've learned today is these are the people that are most impacted.
Yeah.
The health department.
Yeah.
But it's happening.
Yeah. So we don't, like there's what I talked about yesterday, some is like uncertainty in estimates of the projections of climate change, right? And so so we have this computer game, right, that we simulated for 500 years, right? And let's say there's 100 different possible ways the climate could evolve, right? So then we're saying, if we want to test each one of those out, 500 times 100, right? And it's not that fast of a computer game. It takes a while to run. So we're a little limited in the degree to which we can explore uncertainty. And there are other sources of uncertainty. I'm glad you brought up climate change, right? Because I think the number one easiest thing to predict about how climate change is going to impact the West Coast is increased exposure to extreme heat. The water stuff is complicated, right? Yeah. A little, yeah. That's what I work with. The economists are more the public health folks than me, yeah. Okay, so the last piece that I wanted to talk about is this idea of what to do about it. Could you address not just the total amount of pollution that's being produced and exposing people, but also the disparity, right, in who's exposed. And this actually, when we look at it this way, it looks like a more dramatic difference in terms of who's exposed. And the reality is that this pollution is exposing everybody, right, in California, pretty much. So what this is showing, this is without any type of policy in place to try to mitigate air pollution or inequalities in air pollution exposure. If you, on average, an average year, right, there's like 40 million people in California, right? We're saying that each one, everybody in California loses or is penalized, or however you want to describe it. You incur $21.27 of health damages every year as a result of air pollution, right? And that's a weird thing to do, is put a dollar sign on human exposure to air pollution, but that's what economists do for a living, right? They say, okay, like if we can attribute a certain number of hospital visits or lower life expectancy due to air pollution exposure, can we put a dollar value on that? It's at least one way of kind of trying to measure how important it is. And then the difference per capita between people of color and the white population is actually smaller than you might expect based on where the power plants are located. And that partly is related to the fact that when you produce air pollution, it spreads out, right, by nature, right? So everybody's getting exposed to some degree, but there is a difference, a significant difference between damages between these two groups. So what happens if we tax the power plants based on how damaging they are? Meaning, if there's a really dirty power plant, but it's off in the middle of nowhere, and it's unlikely that the air pollution that it produces come and like settles over an urban area, it might be less damaging. But if there's a power plant that's closer to people, or it's upwind of a population center, it would be more damaging. And if we distinguish between those rates of damage for each power plant, and we penalize the ones that are the worst relative to the ones that are not as polluting, and the system operator, meaning the computer model, is constantly choosing what is the cheapest way for me to meet electricity demand every single hour of these 500 years, but it suddenly sees the dirtiest power plants as a more expensive choice. It will choose the slightly less dirty ones, right? And that results in a really big reduction in human health damages, right? For both groups, right? You drop down from a per capita damage of $20 to about $6, right? And this doesn't mean we're retiring fossil fuel power plants or building more wind or building solar. All we're doing is saying the really dirty power plants, we're going to make those look more expensive when it comes to turning power plants on and off and scheduling them. Yeah?
Does that include the cost of the tax?
This is not representing prices for electricity. This is saying this is the reduction in human health damages in dollars. Yeah?
It doesn't look at the cost of achieving that.
Correct. So the paper, right, does explicitly talk about how taxes influence the price of electricity. This makes electricity more expensive because you're saying, okay, it doesn't mean that when you tax anything, right? It makes it more expensive, right? What it's trying to do is change the priority that the system operator has for choosing power plants. But the mechanism that it uses to do that is to make these power plants that used to look really cheap more expensive, right? And so, yes, right.
And it's also a very regressive tax.
You said regressive?
Very regressive. Tax,
Correct.
because the people that least can afford that are the people of color and
Correct.
and not always, but it's a very regressive tax. All the taxes California do are very regressive.
Did you say regressive?
Regressive.
Yes, okay.
And it
So,
affects the lower income people the most.
right.
The biggest percent of their income,
If,
just like the 75, even a federal, the 75 tax
right,
credit on the cars, poor people can't afford the
right.
car, so it's very regressive.
Yeah, so there, and that is a question for another day and another person, to be honest, right? But like, let's say, yeah, so let's say in order to achieve this, you're imposing a tax, right, on these dirty power plants, and the power plants pay this tax, right, and it goes to the state of California or to CAISO or to the federal government. And then they pass that tax on to customers by raising the prices, right? And so that's how this all works. It's a separate question to then figure out how the revenue that's generated by the tax is distributed, right? Same thing with the carbon tax. That's a very important question, right? Because if you use it to reduce the corporate income tax, right, or corporate tax rate, or payroll tax deduction or something like that, then it could have a very different impact than if you just sent it back to individual people or tried to turn a tax that was regressive into something that looks more progressive.
Rolling ones of economics.
Right, and I'm, not the correct person to ask about that. So the last thing I want, so this is on average, some